So during the last lecture we have started with our abstract class interface as a demonstration how such interfaces are generally implemented, and we arrived at some very basic smart pointers at which we can continue today further. So here we have our smart pointer, which we have devised. It is quite flexible already. It allows us to use it mostly like a normal pointer, so it supports assigning and reference counting. Now there is another type of pointers which is quite often used as well. These are unique pointers. The difference here is that a unique pointer cannot be shared amongst multiple objects at the same time. So the idea there is that if you have a unique pointer, you know that whatever it points to, always there will be only one reference to it. This is quite useful, and we in fact had such a sort of unique pointer with our first pointer attempt. So we will just refactor those two classes a bit, and to do that, what we could do is we could introduce a shared parent class, which we could put into our actual interface. So hash include what was the name? Interfaces. Interface H, and here we will define a abstract pointer class. So let's see, that will be viewer for string class template. Let's do two things. First, first we make a class which is just called base pointer, and it will be an abstract class which only will provide a release function that we can use to free things the pointer points to, and gives us some additional flexibility. Then we'll derive a template class which will be an abstract pointer, which will be derived from base pointer. And it will contain, what will we need? Those two functions would be good to have. Well, actually all of them are quite useful. Let's go with them. And the thing needs a destructor. Since this is a template, it will be implemented everywhere individually anyways. So right, now this we can make derived from that interface. This will be seen. We call a unique pointer that is to the template. Abstract pointer font T. here with my pointer. This will be shared pointer. Oops. Okay, let's see. For now, let's ignore this. Maybe we will not need it. Just keep an abstract pointer as a template. But then this will get its own. Let's keep it. Yeah. I don't want to make it overcomplicated. This function which we then will need to implement here. We could just rename the function here. It already does the same thing. This will rename something else. Attach. Okay. Well, first step, checking whether it's still whether it is still working. We need, of course, to change the pointer type here. Here. Okay, it's already complaining about something. Let's see. We are missing something. We are missing. The add operator we have not implemented. We need that interface. We don't really need this operator. Don't really need this. We only need the asterisk operator, the operator, and we need the asterisk operator, not the add operator. Missing. This only works, of course, if we already have something. So taking a reference on we should throw an exception if m does not exist. Although, to be honest, here this thing, when we try to reference to the reference pointer, it will also throw an exception. So this is good enough. If we get a nice defined null pointer at the referentiation error, then this should at least avoid any security issues. I can quickly run it. See if it still works. Okay, there is still something wrong. Right. Too much copy and paste. Okay, one more. Automated private. Oh, sure. Okay, so it's still working. We can remove the DLL loading messages. We don't care for them right now. They're main. And yeah, they're main. Okay. Good. And now what we want to try to do is to see if we can somehow not have to pass a not have to use a raw pointer. So here, let's see, we start with our test case. So we have our interface, and here to set we are passing just a pointer on string. So an improvement would be, of course, if we could use already our smart pointers in the interface, or when we want to get the name, like here, that get name gives us a pointer to a string. If we could use smart pointers all the way and not have to put normal pointers in smart pointers. So I haven't tested that in detail, but I think we should be able to make this work. So we have our get name function of plugin1. For simplicity, let's just add additional functions. So let's go to our interface. Okay, so here, let's start with the set name function. So instead of set name, what we would want to do is here to have a pointer that we need to add, that we need to change the layout because we need the pointer here. So actually let's include help us here and move the pointer thingies here and move the include definition. Then we would use an abstract pointer, set name safe, let's call it. Okay, that would be our function. And for now, let's maybe, so for simplicity, we'll disable the dependency on plugin2 and we'll disable the usage of plugin2 so that we can, so that we only have to do changes in one place instead of in two places all the time. So obviously, when developing some interface, the goal would be to first make the interface final before starting making implementations, because that of course adds a lot of work. So rewriting things is always a bit annoying, so it's good to first formulate a really good plan and then execute it. So okay, plugin1. Plugin1, make plugin here. Oops. This one. Yeah, let's leave it here. So we can just copy the body. And since the pointer works like a pointer and the string type is known, then here this already should be working. So we just need to put our test case here and where is it? Set name. So this works still. So the difference is, although it might actually now complain that it is ambiguous. Let's see if it does. Oh yeah, right. I should just build this one. We don't want to build plugin2. We are missing something. That was one mistake. That must be, of course, a reference. Otherwise, it would need to be fully implemented, and the abstract point obviously is not. Interface here. Okay. Alright, let's see. This is of course not the file name is wrong. It should say set name safe. So it won't be ambiguous because you use a different file name, a different function name. What we also could of course do is to remove this operator here. Usually you would not have such an operator on a smart pointer because you would not want to allow accidentally giving out the raw pointer to something. So for safety reasons, you would have a function that would allow you to do that, but at the same time you would not want a automatic cast operation. So let's comment this out and add a function to get it. Get raw. Yeah. It should still compile because I don't think we used it. I'll use it somewhere. Alright, we had this in our template, so we need to of course comment it out here as well. And here a unique pointer, it's also not the safest thing to do, but let's add this get raw. Actually we could add this get raw and also to our abstract class here, so let's do that. Okay. Now this detach, as you might remember, its function is to allow us to pull out a raw pointer from the control of the unique pointer such that we could assign it now to a shared pointer or do anything else with it. So this will not be common. So such a function would not make sense in the shared pointer, since a shared pointer may be shared, i.e. we don't know a priori how many other pointers there are which still point to this object. A practical option would of course to add here a variable to get the reference count so that we know, but this would not be ideal, so to say. It would work, but when you think about your implementation, so if you know that you cannot use detach, what do you then? In special case, it would be useful. You could opt to make a deep copy of the object, but it would not be very useful in a generic case, so we will not add it here. So let's continue now with our interfaces. So now what you would need would be a get name safe, and there is one limitation. The pointers need to be with this abstract pointers, this will not work well across a returned value. So what we do is we just pass the pointer as a non-const reference, and then we are on the safe side to use it as we want. So here, get now just pen name is equals make string set string, and we don't return. This needs to be the pointer. We have the helper here. What is make string returning? Make string is returning just a string pointer. So the abstract thing does not have a constructor. So let's add a function to it. Punct set raw, which will take this job interface, help us void set raw t asterisk ptr. Okay, so now obviously this will need a set raw as well. And the same thing for here. This it's assign is not correct. Attach. Oops. Wait, no, attach. Attach is not correct. We need to actually do this function. Okay, then let's go with that. Attach would be nice. We'll make just a second attach, which we can use that as the same, or attach raw. And same thing. This is set to null, so we can use attach raw here as well. Since m is null, this will not be as efficient as it could be, since when we enter here, and then we exit there. So we do some extra computation, but we make our code much more elegant. So I think this is a worthwhile trade-off. And of course we could have just called the function setRaw directly. But now, since let's do it this way. So this way the mechanics of the smart pointer with regard to the mechanics of the interface is separated a little bit. So this should be nice enough. Okay, I have a typo, I guess, somewhere. Alright, the get row here is of course different. It's just ptr. Oops. Oh, what happened here? Okay, working again. One thing here. Can decide what we like. That looks better. Okay. Good. So this already gives us some even better functionality. Now we can handle pointers. There is one, let's say, main limitation that we still have here not really solved. That is that if we would assign pointers here inside this thing, so if we would create not an abstract pointer, but for example some other instance of a pointer and try to assign from it, then it would use an internal object created in the plugin. So generally this is not perfectly safe. So what I mean is, let's make a short demonstration. Let's add a function. Let's add the pointer here. Shared pointer main string test. Oops, test, not text. And let's is that complaining? Oh, we don't have a default constructor for this pointer. That's not great. We want to be able to create those thingies without anything. So let's add a constructor that doesn't do anything. Right. So we have our constructor. Then here we can assign our setRaw make string we should add to it some text set L. Okay, so we have our internal pointer, and here we have so here what we could do is just for demonstration one might want to do such a thing, and outright demonstrated best. So let's say we put a breakpoint here. Okay, so we are here in the plugin, and then we are entering the make string we don't care for, entering the point, and as you see from the stack trace, we are still in the plugin at one code. We are not in the exe. And then when we enter here this attach, then it will first try to release, but there's nothing to release, and then make new, still here inside the plugin code. And then we get out of this, then I put a breakpoint here. Why didn't we use that? Oh, we didn't use the get safe name, haha. Right, yo. Interface get safe name pointer. Okay. So we will not step through that. We already seen this. Then we are here. We are still in the plugin code. Then we enter the thing. And then here it didn't step into, so we need to open the we did not define an assignment operator. That is a problem, because the thing here, if it does not have an assignment operator, it will just do the default assignment, which is not good. That is not quite ideal, because the assignment operator, as it's here, it returns so the type that we can use is fixed, so we cannot use an arbitrary type. We need to use this shared pointer, but in the template this does not yet exist. And if we just add a assignment operator in here which returns unique pointer as type, then which returns abstract pointer as type, then this will not be overwritten because this has a different argument type. So what we could do, of course, is we could add a assignment operator, which will be just a dummy, the one that should not be used. Let's for now just add one as no, we don't like that. One thing, this will not be safe. This will not be. So one problem with C++ is that you can add a lot of conversions from different types to each other, or different assignment operations, and at the end you might end up with code paths taken that you did not think about while creating those conversions. So here what we could do that might work is we have this then we also would not have any type checking. So what you could do is we could have a set, well, not raw function, which then would be implemented within the template, which implements the actual pointer. So for example, within this one, and then typecast the abstract pointer to our own type. But this would then allow us to assign any type of abstract pointer to the other, and this would not be it would not be good because we would lose the type safetiness. So I actually think this this demo we should not do. One thing we actually, however, should do is to ensure that such an assignment like here cannot be performed, because if you do it, as mentioned, it bypasses the assignment operator and it bypasses the reference counting. So to make our thing safe, what we will do is we will add a assignment operator which should not be accessible. So here we will make them private, and this thing should still be virtual. And for now, let's comment this one out, because otherwise I need to make all the changes on both own implementations. That is a bit annoying. So we have here this, this is not shared pointer, it's abstract pointer. I don't know, that should work. Maybe it will work. Let's just try it out if it will cause issues or not when we try to add this operator, because it's already an abstract pointer of a given type. So this might actually just work. We still need to typecast it. It is the not so safe. So basically, other should not have a M. It doesn't, so we need to typecast this. Asterisk reference other arrow M. Now the assignment will work, but let's see if this will be safe enough, because we always get the type abstract pointer back and no longer the type shared pointer. This will, however, mean that if we want to make assignments, we also need an assignment operator that can take an abstract pointer. Okay, let's see. Also, that's type that should be cast. Oops. Right. Okay, so this we had, and now let's see. This works, so this now works correctly. So we do the release, we assign M, and what we now should remember is that the M that we are assigning now, the pointer that we are assigning now, before when we created it here, it was created with code from the plugin plugin 1. So the structure of what M contains is, so to say, it's fixed, and we don't have the, so if you would ever change this structure, then you would need to recompile all the plugins, because as we will see in a second. So we get out of this, we get out of this, and now we have this arrow operator here. And now as you see, we are arriving now at code from the main executable and not from the DLL which has created the M variable. Now, as long as the M variable looks exactly the same in both implementations, this will work just fine. But as soon as we would have a different implementation for this M, then the whole thing would fall apart, and we would not longer and it would not longer work correctly. So I mean, this can be of course demonstrated quite easily. So now it expects this order and it works. So if we now turn off the dependency, so it will not rebuild the DLL, and we change the order here, and you try to run it, it will most certainly run into a crash at some point, and voila, it crashed. So as you see, when doing such things at some level of complexity, there is a need to be careful with how those things are being implemented. Of course, we could make the shared pointer even more complex. We could in principle implement a abstract interface for this as myPTR, and then we could of course abstract this even further away, for example by creating these MPTRs the same way as we create the strings, so that they will always be created from within the main executable, and the main executable will keep track of them. This approach would be relatively secure. If this is interesting, we can continue with that. Another thing we could dive into would be weak pointers. So a pointer which is implemented such that you can basically, if you have like weak pointers referring to an object, which let's say you have a weak pointer and a shared pointer referring to the same object, and when the weak pointer goes out of scope, nothing happens. If the shared pointer goes out of scope, the element gets deleted, even though the weak pointer still refers to this element. So what is done in such situations is that on the weak pointer you don't have this operators that would allow you to access its content. You only have one operator to create a non-weak pointer from it, and this operation is implemented such that it either will succeed and give you a strong pointer to a valid object, or it will give you a null pointer in case that object already went out of scope. So then you would need after trying to obtain such a pointer, always check whether it worked or not. And such weak pointers are quite useful if you have objects with references going multiple ways. So for example, you have a tree structure and you have, let's say, of course the parent node will have a list of pointers pointing to the child nodes, but you would also want from the child node a pointer to the parent node. And you could either use a normal raw pointer for that, if you can assume or make it certain that a node will never go, so that a parent of a node will never go out of scope without the node itself going out of scope. Or you could of course implement some code that if the parent goes out of scope, it sets the parent variables in the children to null. So this would also be an option, but this is somewhat a manual operation. You need to think about it, you need to take care about it. So implementing the back reference to the parent using a weak pointer is a very elegant solution, because assuming the nodes go out of scope together with the parent, then it's not a problem in any ways. And in the other scenario where if the parent goes out of scope, you want the children to remain with a null pointer, this is kind of automatically taken care for you by you and washed. It happens on its own. Let's say it's automatized. So this is quite elegant, and generally you might have heard that in the US now there was some memorandum from the government that they kind of want to know from all companies that are using memory unsafe languages how they intend to mitigate it, with the goal of, okay, let's not use C++ at all. But this obviously is unrealistic, so now there are attempts to make C++ into a memory safe language. So there are a couple different approaches. All of them, so ideally the best approach would be the safe C approach, where you kind of just use the tools that C++ already gives you, and on the compiler level you implement only a flag that will disallow you to use the unsafe thing. So basically you would write such a pointer class and define this as, well, not normal C. So this will need to be tested very thoroughly, audited that it really is flawless, and then somewhere in another class like here, for example, you would define this as a save save C++ file, and then you would only be allowed to use this previously defined and created smart pointers. You would not be able to use raw pointers or normal C arrays and other unsafe constructs of the language. And the main idea here really is that this way you can port old C code to a safe version of it without a large breaking change. And as mentioned, for this you would need such weak pointers as well. The standard template library provides its own weak pointer implementation, and what we could do here also is add such a reference counted such a implementation to our thingy. So let's see. So basically, when you're creating a weak pointer, what you would do is you would extend this reference counting structure so that it holds not only references, well, strong references, but it also reference counts the weak pointers. So we could do that. Thinking how to make it most elegant, because like on the STL uses really two independent counters, but I'm not quite sure how best to synchronize them with each other to avoid a situation where one would end up without where one would end up without those two elements getting out of sync. So one could of course use some thread synchronization to lock multiple objects, but this would not be very performant. So we could use a total counter. Yeah, we could use like one counter counts all the references and the other counter counts only the strong references. So let's call the other one which one is that? Just weak. I don't know, you write weak like this. I think you write weak like this. That was like weak. Well, let's call it total. Yeah. When do we use this? Only there. Okay, so we could actually rename both strong refs and total refs. Okay, so of course, if we are creating something new from scratch, we just set both to 1. This is trivial. Now, if we are attaching an element, we'll have to increment. This is also trivial. This does not pose a risk for anything bad to happen, since we already have at this point a strong element keeping track, and then the release object will be more interesting. So we have two scenarios. This will be the strong ref, and if we decide to delete it, we delete it. Oops. And we set this to null. But whether we can delete the actual parent object, that will be a separate operation. Let's copy this. This will be the total references. So we are decrementing the total references, and if wait, no, we need that check actually. Oh wait, there is a copy and paste bug. Strong ref, this stays as is. This goes out. Copying and pasting is dangerous, but I think I mentioned it already a couple times. Right, so if total ref is now also reaches 0, then we can delete that, and we always set it to null. And this one, of course, here we need to set this to null. Null ptr. Although at this point this should not be accessible anymore because it's 0, but we just set it for good measure and easier debugging. Okay, so let's create our let's go until here. We need that as well. Let's copy the whole thing. Okay, so weak pointer. It's 11 and we would not derive it from an abstract pointer because we don't want to have to fill in those, at least some of those thingies. And this we also don't want, so we only want to create such a thing from a shared pointer of our type t. This will need to be revised, attach, release. Okay. Assignment operator. Oh yes, that is good to have. Weak pointer. Oh, this one needs to be. This one needs to be changed as well. And we want to have two assignment options from a shared pointer as well as from another weak pointer. So there will be two assignment operators that take different values. And it's the same m, so this is fine. Then we need release and attach. And m. Great. Both need to be able to access this, so this will no longer be an internal structure. This will be defined somewhere here, and we should rename it to something. As pointer data. Smart pointer data is smart pointer data. Yeah, that's a good name. And this needs to be a template, of course, as well. Oops. That's not how we make a template. That's how we make a template. Okay, so this will now need some copying and pasting. So zack, zack, zack. And we will need probably to add t to all of the definitions. T, okay. Right, the contents we need of those functions we need to adjust. And we'll have this function that will give us a smart pointer, a shared pointer, t acquire. I'll call it acquire. The other names that you can give to such functions is, for example, lock. So STL uses lock for whatever reason. I mean, because it kind of locks the state of the shared pointer. So if it was still existing, then it will keep existing, so to say. I don't find the lock name particularly intuitive. Acquire is, I think, much better. In principle, one could also make a cast operator from this to this, and then it would just do this acquire operation internally. We might do that later. Okay. So first of all, attach. Attach will not increase strong references. That's important. It will only increase the total references. And here, if it is released, we also only handle the weak reference. We are not touching the strong reference or the data object. The only place where we would acquire it is here. So let's think about it. The main difficulty with designing such things is that you want them to be thread safe. So you want to ensure that if you have multiple threads doing multiple things, that you will not run into a situation where you will end up in an inconsistent or unpredictable state. And in our case here, the problem is that we can sit in one thread which uses the weak pointer and will want to call the acquire function, while there is another thread which holds the last reference to a shared pointer, to the associated shared pointer, and exactly at the moment where we try to acquire it there, it tries to release the element, so that we implement it such that we can be on the safe side, that we will not end up with some sort of an invalid reference. So on the level of the normal shared pointers, we ensure this by two things. First of all, that we actually are holding one shared pointer right now while we're creating another one of it. And the second thing, of course, is that we're using this reference counting which works atomically. And this long is since it can represent positive and negative values, we can exploit that. So what we would want here, at this point, since we are inside it, we know there is at least one valid weak pointer. So we know that M is valid. So we don't need to worry about M. So one thing we can do, of course, first is we can add ref to M. Although at this point we don't care because we might want to return a failure. So what we should first focus on the strong reference. So what we want to do is we want to basically add 1 to the strong reference, and we will need to check the returning value. So what we expect is that if we add 1 to the strong reference, at the moment where we started add this operation, strong reference was at least 1. So if the resulting if the resulting operation of add 1 to strong ref would be 1, or well, if the value is like negative, then it could be 0. But let's assume it was 0 because it just went out of scope. So at this point, the resulting operation will be 1. So if this is 1, this is an error case. We don't want, in this case, even in this case, basically what happens to the data we were supposed to access is already undefined. So we cannot do anything with those data. So if this happens, then we will need to dereference that again. So -1. So return it to 0. And we will just return an empty pointer. And we will not change M. We will not want to increment the other reference count, because at this point we are just assuming at A the M is still being taken care of, because we are inside one weak pointer, so that is not our responsibility. And secondly, we don't want any responsibility here because we couldn't acquire the element. Yeah, so of course 0 would, we could of course change this code, like if it's less equals 1 to be safer, but technically we should at least in the debug build have somewhere an assert that if this would for whatever reason become negative or look like it was negative before the operation, then we should throw an exception, because obviously something else went wrong at some earlier point. The problem is that the earlier point might be some longer time ago somewhere else and we just didn't catch it. So well, this much to our error case. And on our non-error case, so we know we have incremented this successfully, so the next thing obviously to increment will be the total counter, and M we can set not our M, and we can create that is okay. That complicates things. We need a way to set to from from within our shared pointer. The problem is, since everything is with templates, we cannot just define this as a friend here. So usually the proper approach would be to add another level of abstraction. But that sounds like too much work. So since we first want to demo it, let's do it some simple way. Because I cannot use set raw, because that would not keep track of m. So we will make here some test function void set, or set m. I will just call it set m. I mean, the other option would be to just remove protect and use attach. That is also maybe an option for now. We'll just remove it, protect, and then I can just attach the thing to our new pointer. So here I create a new pointer. Which will later return. And now we just punct attach m. And if we do it this way, the problem will be that attach actually performs this incrementation as well. So in this case, we would then decrease the incrementation that we did, so that we can ensure that the thing will end up at the right value. And I think about it, if we go with this approach, we can make the code a bit more elegant. Because we always need to return something. The only question is whether we do attach or not. So we will take this code, say that this must be greater 1 or greater equals 2. Greater 1 is nicer. So if the result is greater 1, then we know, okay, before we did already 1 existed, so the thing exists. Then we attach it, then basically it will take, this will turn rf greater 2, strong f greater 2, and this will remove the reference which we added before, which is no longer needed. And in case when we fail this, then this is not done, this we still need to undo, and then we just return an empty pointer. Nice. Okay, let's try it out. So just for simplicity, let's just play around with a string. Let me have a typo. What was the name of the string? My string. I don't remember. My string. My string. Sptr1 is equals. We can make a string. Right, we can make a string, and we should assign something to it. Set okay. Do we have a reset function? We should add a reset function so that we can easily clear those things. Void Apache Gateway void. Reset. Or we can make release public. That's better. Let's make just release public. That we will need to change less things if we do it this way. Okay. So here we can release this thing. We can make a copy. 2 is equals 1. So then we would do something with this. We only have set. It's boring. Just undo. Let's not do anything. we have released one, so when we go out of scope of this, of both, that should reference everything, but we want to demo our weak pointer, so let's define here our weak pointer 1, ptr2, and wherever we can assign it here, for example. But of course, when we try to lock it here, okay, that will be a good demo. This will be number 3 is equals, this should be okay, pointer, that's weak, point acquire, and here we can actually use the wv pointer as well to acquire something. Oops. So this operation should work. So here let's we have a get. Oh, it's a C string, so that we can demonstrate it was fine. We have get data. Okay. Right. Then the thing goes out of scope. So one gets released, but the data still exists since. Actually, I can use this here for demo, since pointer 2 is holding the reference still. And here, this should be, so if this, then printf, because it should not exist, fail. Okay. Good. Breakpoint here, and we can run it. Okay, we have a issue somewhere. Weak pointer we don't derive from anything. Okay, and well, it said it did what what I say it said it would do. So let's put some breakpoints here and there and take a look for everything. Okay, so here we are entering our acquire function. We create an empty pointer. Then we see that strongRef is 1, so if we execute it, strongRef will be 2. If this gets executed, what out of that, strongRef will become 3. And then of course we decrement it so that it's back at 2. And this is correct since there is one pointer 1 and there is now the new pointer ptr. So if we now step by step, we're arriving here. Then we can release pointer 1. So we just see that this was 1. It's now 1, so we didn't do anything. This thing has 3, so it will not do anything. It will just go back down to 2, obviously. And now we print it. We don't care for that. Now we will run into the destructor of sptr2, which does release. Again, this thing is already 1, so it will be disposed of. Don't care for the delete me. And this one, since it's 2, it will not be. It will be just decremented. And we continue. And at some point we are done. And here we are again now trying to acquire, so let's repeat that. We don't care for this. So here we see this is already 0, so it will become 1, and 1 is not enough, it must be more than 1, so at this point we go back on the operation. And when I think about it, this is not perfect, because it will be intermittently 1, and this will not be good, because if at the same time another one would try to lock, it would think that it is valid. So that is not yet a perfect implementation. But anyhow, we return a null pointer, and if we continue somewhere, if we can go out of this, we don't care for those things. Just want the destructor. Okay, right. We arrive at the destructor of one shared pointer 1, but it should already go out of scope. That should be released. M should be null, I think. It doesn't show, but it must be null. Yeah, M is null. And then we will enter the weak pointer destructor, which will then take care of dereferencing this. And then we are done with the function. We had another one. Okay. And yeah, so the problem that we are still facing, which I just noticed right now, is that here this implementation is not completely fail-safe, because I said if we call not here, where's this acquire here? If we call acquire on 2, so from 2 threads on 2 different weak pointers at the same time, then we might end up in the scenario where this is not one, where we will get 2 as a return, because between this line and this line a lot of things can happen. But I think I can fix that. Can I fix that? Let's see. We will try to use other atomic functions. So we will define this as volatile as well, so that we can use atomic operations on it. And okay, so we need to ensure that we will never run in a situation where we would have an invalid pointer. I mean, if we would do this and the pointer as such would be null, it would still end up in a semi-valid state. That would not be great. So let's see our release operation, and what we want will be here. So t asterisk so first we make a copy of that pointer, then we make then we check whether this is null or not, because if it is null, then we don't care either way, then someone else is doing something and took responsibility already. Okay, so we know the value that it should have, we know the pointer thing, then we'll use interlocate, what was the name, compare exchange. I think there is also a pointer version of that. I mean, interlocate compare exchange pointer, that one we want, and we can just pass to it a void pointer. So we want to set this to 0. So we exchange with null ptr, and we compare it with what it was before. And what we get, what does this return? Probably the current value after the operation. Let's see. To look at compare exchange pointer, return value. The function returns the initial value of the destination parameter. The initial value, okay. So this thing on success will return the same value that is in pointer, or that we expect to find in pointer. And on failure, well, if it's initial value, then it's initial value. So let's this can be void asterisk. Okay, so this thing guarantees. So the way this interact compare exchange works is that it guarantees us that the operation will not be interrupted. It first will compare. This needs to be a reference, I think. Yeah. First we'll compare the memory content at this address with the value to compare to, and if they're the same, then it will exchange it for null pointer. If it's not the same, then it will not do anything. So if this thing gives us the initial value, then and this is also should be atomical, so we can repeat the comparison. So if this is equals that, then we know that it now is null, and we can get rid of it. And if and we don't need to set null because this already has been done here. If someone else did replace with null, then the original value which we get here should be null, and then we don't do the second part of the operation. Okay, so this ensures that we are on the safe side. Okay, and can copy this part of the code down here, so downward down here. So again, we start with but we don't want to set this to anything. We just want to ensure that the other one let's say the other thread will do the assignment at the same time. It's still not perfect. It helps us in as much that we know that this thing will not become unexpectedly invalid. So there is only one thread which ever could delete this reference. It cannot happen that two will try to delete this reference at the same time. And let's say that we have two threads trying to acquire this can still become one. What we could do is we could just ignore this operations. We are both in a weak no, let's keep that. Let's keep that. So we did our strong ref. So now after strong ref has been executed, it is certain that it will not, that nothing will get deleted. It might have been deleted before, but afterward it will not be. And now in principle, if this is not null, then we are already happy, because m is always valid, we said. So if pointer is not r, then we can actually do the attach. And now if we would have, if we don't actually care for the return value, because as said, we might find ourselves in a scenario where two try to increment at the same time, so we do this only to lock it, to prevent it from being deleted, and then we test whether it actually was deleted or whether it's still around. If it is still around, then it should be safe to use. Is that correct? That was 0. And if this, so let's say this decides, not quite, because we could, no, we just lock at some point. We could do this lock. It could happen somewhere at this point in the other thread. This is not good. I could look up how STL implemented that, but I'm trying to figure it out right now. I can find a smart way without too much locking. I mean, the other option, of course, would be to just synchronize access to the object and use a spin lock, but that would be inefficient. So I'm thinking whether there is some trick to ensure that this works. There actually is one, and actually we did not need to. Oops, I pressed something. Actually we could do it differently. So for now, let's comment this out. Let's go back to the initial implementation where we just deleted that thing. The thing is, we have certain expectations, and if something happens asynchronously to what we expect, that might be a problem. So basically, what we want here is a proper expectation management. So this doesn't need to be volatile. Yeah, because that would be the other approach. We can use this trick here, so we long sref count, make a copy of the thing, then we do this will be expected strong reference count, and we'll have like look at compare exchange reference on this thing. Now we want to exchange it with this +1, and we expect it to be this old value. And now if everything went as expected, if old reference is like compare reference, well, and of course two things. If this is 0, then we don't need to do anything. So if this is 0, then we just return the empty pointer. And if or actually we should say less equals 0, or we could just say less than 1, and then we just break if this happens. So if we were successful, then we can do the attach and return the pointer we have here. Actually we could restructure this maybe a bit. So if this is greater 0, we continue. So we take a copy, we check if it's greater than 0. If it is greater than 0, then we have a chance on success. This ensures that our expectation will be met. It could happen, of course, that in the meantime this thing drops either by 1 or gets increased by 1. In principle, increased by 1 would be fine, but we don't have this level of control in our atomic operations. We don't have like interlocate compare less than equal. I think there is no such instruction. So if this is false, then we will need to repeat the whole operation. So let's put a loop around it. Just make an infinite loop. And on success we break in two scenarios. We break on success. We only continue actually on we only continue if this is not right. So we could say here break. So if we arrive at the end of the loop for whatever in this if we arrive at the end of the loop for whatever reason except one, we want to continue. So if we were here, we want to continue. If we did not enter this, if we were here, we want to break. If we did not enter this, then we also want to break. But if this thing here was unequal, we want to continue and try again. And the way this mechanism here works is a kind of like a spin lock would behave, just that a spin lock would have the purpose of actually locking execution, while here we are just repeating the attempt a couple of times until we either succeed or we hard fail because the element went out of scope while we tried to acquire. We tried to grab it, but it was getting out of scope faster than we can try to grab it, and then we failed to grab it. It's not perfectly perfect with regard to the behavior, because you might say you would want something that will give you in any situation a good chance of getting the element, but realistically you probably are not trying to grab something that just goes out of scope, because this again would somewhat be an undefined behavior. So you would usually only focus on the static situation for whether you want to have success or fail, and you need to handle these dynamic situations only to ensure the consistency of your pointers. Okay, let's just try whether it still works, or whether I broke something. We don't need all these breakpoints. Okay, so it said fail, then something is wrong. Then we need to debug this. Right, we forgot to decrement it after attach m. That is a minor inconvenience. Right, so if we succeed to attach it, then we need to decrement it by 1, since we first try to capture it with our incrementation approach. Now it should be fine. See, testing the code is always very important, otherwise there might be unexpected bugs. Good. Good. Very good. So as mentioned, what we are missing here is some solution to allow the weak pointer to do the attach on the other pointer. One way to make it semi-elegant would be to implement here another constructor which will just take a basically I should have copied this one. This was almost perfect. Just that we use here a reference on the m. To use the smart pointer data, we don't use the shared pointer data, so we just attach m. Okay, so here in this case, where are we? We cannot longer attach, but we can do it like this. This is equals m. Okay. It's all commented out. Why is it complaining? Hmm? Spirit only. Release is became private. Yeah, sure, because it's in protected. We said we want this public. We want release public. The other ones will remain as they are. Shared pointer, it has the constructor, it should accept that. Shared pointer data of type T. By reference, that should be all fine. Wait, but it's const. It will not want, this one doesn't take const. Let's just like this. Wait, that takes a pointer. That was the problem. So this needs to be a pointer on M, and here to reference M. That's why, as you might notice that now it is just okay. I changed, but before, as you have seen, it was pointing us to some completely wrong place. So okay, it's still doesn't. So sometimes it's not perfect. So let's see. Right, M is already a pointer. Then that was fine. Okay, closer, but no cigar. Unresolved external symbol. Shared pointer operator. Not implemented abstract pointer other. We have some problem with our assignment operator, which we have put into the template further up. So these linker errors, they are always a bit cryptic, but we can take a look on it in detail to try to understand it. Let's go here and open the comments. So first of all, let's copy the whole thing. So we have an unresolved. It's a good exercise because such errors, they are really a pain to debug sometimes. So we have an unresolved external symbol. This means that somewhere in our code we say there should be a function with this prototype under here, but it does not exist. Okay. And in this case, obviously, it's a bit long, but it's pretty much what we want. So it must be a public. Now a virtual function in the class abstract pointer, and the name within the class will be the assignment operator, and then it has some decorations which we don't care about, And then it says where it's referenced. So it's referenced in function public void shared pointer assignment. So the thing is, it expects in our assignment operator for shared pointer to find and access an assignment operator for this abstract pointer. Help us. Why does it do it? It should also, and unfortunately, since it compiled, it does not tell us which line of code is responsible. That's the most annoying thing about debugging such link errors, that you need to think about it from where this error actually originated. So let's go to our assignment here. So the prototype extra. Oops. So apparently there is somewhere a assignment operator for our native type, but it kind of is not fully working, and the reason will be that we did a small mistake when we added this function. We should have added also the shared pointer version of this function, and because since we didn't add it, the compiler generated a default one for us, but the default one uses the default functions from the parent class plus the default assignment operators for members if there are any. And in this case, it wanted to invoke this assignment operator, even though it is a virtual function. It does not exist. As you see, it's equals 0. So it just is not there. But when the compiler generates code, it doesn't do as many checks. So if you would try to invoke this thing, it would actually give you a compiler error. But if the compiler tries to use it on its own, then it doesn't notice that it is invalid, and then you end up with this thing being missing. But now, since we have an own assignment operator which does not refer it to the parent object, then it should be fine. Almost. Somewhere is not quite right. Something is not quite right. So didn't we set this to null? You were. We did not. We forgot to initialize it, and then of course when we tried to do something with it, it unfortunately crashed. And here we should set this to as well, just for good measure. Okay. Zack. Voila. And it's working. So we have successfully run into a couple pitfalls regarding to using such interfaces already. So I think this is a very good demonstration, as it really demonstrates kind of by doing what you can do and what you can do wrong, and how to see that something went wrong. And also the reason that is so easy to do things wrong in C is why especially the STL library is so limited with regard to what it allows you to do. So for example, allowing to assign this abstract pointer here already adds potential additional pitfalls, and as mentioned, it also is complicated in as far as that different code paths might then handle. So I think what we could try, if we want to really make this pointer working brilliantly, is to really implement a mechanism for this smart pointer data to be generated in one place, and for them to have an own delete mechanism. So this will increase, of course, the complexity, but it would give us a truly flexible pointer implementation. Just thinking what else we could improve, and if we want to improve more, so in principle, what we could do is we could get rid of this abstract template here and instead just define a interface for a shared pointer like we did with string. And then always generate those pointers using some own object. The problem here will be that we will need definitely will need a global object that will be then accessed by all of them. So in principle we have such a global object in our plugin, this thing here, and then just everything can access this and voila. But if you would want to do it from the pointer, that would add some additional complexity. So on the other hand, we have about 15 minutes to half an hour time left. Every pointer took a bit longer than I expected, but at least it's working hopefully reliably. Right, we can get rid of this since we do not need that. The main difficulty with engineering this in a most elegant way is that usually you would not want to have any functions on the things that you are passing across the interface directly. Only if you have a pointer to something that was created the proper way as well. And the next thing is, of course, that for these objects you cannot properly rely on the destructors, the default destructors, because they are not guaranteed to do what you expect them to do. And I will show you another pitfall where one can fall into when trying to work with this object. So just from a formal standpoint, we needed this abstract destructor here, but this virtual destructor here, but it's not equal 0, so it's not fully abstract. So there is an empty function which just jumps in and jumps out, and technically this does not adhere to the definition that we would want to have only virtual functions on our pointer interface, but we needed that, and I will show you with a demo case why. So let's say we create a class C1 which will have a public constructor and a virtual destructor. A virtual constructor, virtual destructor, and then it will have let's say we will add to it some functions. Let's say we make a virtual release, virtual void release, and then some virtual void init. Okay, then we copy the whole thing. We make C1 public C2. Oops, that's the wrong way around. C2 C1. We adapt this to 2, and then we keep those functions, all of them. We will want to use them from here. So let's say right, and we should also have like some demo function just to demonstrate all the cases. So void virtual void test right, and test, okay, test is not virtual, or is it? Let's keep it virtual, and then we need a second test case, second test function to demonstrate. So test fx. Okay, so test just calls test function, like in constructor, the structure just according to the init. So let's add printf c1 test fx \n semicolon. Then we add a printf to the other ones, just with the right names. And we copy all of that and just change this to 2. Not this one. Only the invoked functions. C2. Okay. And let's C2 asterisk pass C2 is equals new C2. Then this one's supposed to be P. In P C2 test. We could make the other ones protected. Don't want them to be accessible from the outside. And a space that it looks nice, and then delete C2. Right. So let's see how this looks. So naively, one might think, since everything that we are calling is virtual, we should get C2 versions of the function always invoked. I mean, we can even add here override. I mean, that doesn't change anything. It would just give us a compiler error if there wouldn't be a function to override. But just to make this as explicit as we can, let's go this way. And let's run it. Let's see what we got. And what we got is not what we expected. So inside our constructor, when we called init, even though the normal behavior inside the virtual function when you call some other function is to call the top level function of your last descendant, in the constructor and in the destructor this is not the case. So in the constructor and in the destructor, this fails, unfortunately, and it's not that unreasonable that it fails, to be honest, because you have, if you want to destroy things, you have the constructor and destructor for your top level function. So you could just move this here, and then it would work as it should. But obviously then the problem is that if you, at least for the one, and we could do the same for the constructor, but then of course the problem is that you cannot have like a functional C1 that does the same thing. So the problem here, which we had here, is that if we would leave this, would try to have like this thing call release, this thing would not be able to call release because it would never be able to access the release instance of one of the derived functions. And this complicates improving this behavior complicates improving our smart pointers significantly, to an extent where I guess I will say that we probably cannot easily make them behave and work correctly as an abstract interface. Because what you want from your smart pointers is that if they go out of scope, so if the built-in destructor is called automatically, that then they can clean it up. And if you would have this cleanup function only implemented in a derived function, then in a derived class, then this will simply, as we have seen here, will fail. So in this way, for example, if you would want to make something derived from our shared pointer, which does a release here, we could not overwrite release anyway, because then the destructor would no longer properly invoke the right release version. What one could do to work around such situations is to do something less than elegant by hand, and we can do that. So let's copy the whole thing. So let's keep this like a one example. Hash if 0 hash else hash if. And now we will try to get the behavior we want. So for the constructor, there is it would be doable, but it will be even more difficult, so we will not do that. Also for the constructor, we usually, to be honest, don't really care. For the destructor, we might care. And the thing is, so the way we would want to do that is we would kind of want to implement some own mechanism that would replace the jump table used by this virtual interface normally. Of course, this is not something we could reasonably use across different binary images, because it breaks the pattern of just using a virtual abstract interface. But for our purpose, if we are within one application and have a use case where we would want to be able to invoke a different sort of cleanup function, then for such a case, this is a workable solution. So we would, in this case, it's a bit boring, but let's type def asterisk p release, and it doesn't take anything as an argument. Return type. Okay, so this is our type. Then we define our mRelease, and then to be able to assign something to it, we would need this would need to be static. It would no longer be virtual. And then what we would do is, in our constructor, we would do, let's say we do init. Then we assign release is equals, so mRelease is equals release. And here, of course, static void, that should be fine. Like if you have brackets, then the function is invoked. If you don't have the brackets, it's the address of the function. So here we have a function pointer, basically a variable which is a pointer, and if we apply brackets to that pointer, if the pointer is of a function type, then it will be called. And now obviously here we would do the same change. Our release would be a static function. It would not overwrite anything, it's not virtual. And here we don't do anything. So here we only need one thing. We change the release to our release, and the destructor stays doing nothing. Okay, so now if you run the example, you will see that for the destructor we called the right version of release. Obviously, when you think about it, there are good reasons why they made such a behavior, the upper behavior, the default, because usually you will here initialize some things. Here initialize some things for class 1, some objects. Then you will clean them, and inside your next function, inside your derived thing, you would again initialize your own things, leave the initialization of the other things to the parent class, and in the destructor only uninitialize your own things and leave the uninitialization of the other things to the other class. So normally this is kind of reasonable the way this behaves, that you have like with the constructor, all the constructors of parent class are invoked first and your constructor is invoked last. And with the destructor this works kind of the other way around. So while a normal function like always overrides whatever it has, so if we would call fx2, we never call fx1, but if we, okay, maybe I should actually add here some more, so let's switch this to 1. I will add here some more printf so that we see what's happening in more detail. Right, this function we did not need to be virtual, so we don't care. This is fine. Okay, this then I just copy this here, delete what I don't need, and change the names to, okay, that I think copying just the 2 lines would have been faster, but after 2 hours of thinking I'm also a bit tired. Right, okay, so we run it again. Okay, so I forgot the backslash ends. No, I did not. Should be fine. So we get into the first constructor, then we do its init function, then we come into the second constructor. So the constructors are chained one after the other, and with the destructor, if it's virtual, as it is, it first executes this destructor, and when it does this, it also kind of restores the previous jump table. This is why this function gets well, all of the functions technically, but this one is one we care for, is then redirected back to this one, and then the next destructor is invoked. While if we call a normal virtual function, not the destructor, then the function just overrides the previous function and doesn't do anything and doesn't call it. We could of course from here, if we would want to, explicitly call the function in the parent class, but that would require from us an active action. We need to write this function in here. While with the destructor, this is always automatized in a fixed order. Okay, so let's do this. So now going back to our example, the question would be why we would want to override the destructor for the final cleanup. This sounds like it's a good way to get into trouble, because basically all the memory which C2 has had allocated and was using after we have exited the C2 destructor and went to the C1 destructor, all that memory is already technically invalid. The block was not yet deallocated. The whole block will be deallocated once all the destructors finished, but the content of the memory is considered garbage at this point, or was overwritten with some marker value. So if it's a debug build, indicating actually that it was already prepared for disposal. So in which case we would want to do that. And one use case that comes to my mind is if we would have, let's say, some inner data structure, my data, which contains doesn't matter, int a like 1 and int b like 2, let's say. Not the best example. Let's go with my strings, because especially ints are kind of boring. So see my string A and my string B. Don't we have a default constructor for that? The string implementation, my string implementation. The interface only is what's the English word for that? It's not valid. Okay, I will make sense of it. You can use such a interface only for pointers, since it has virtual functions. You cannot use it to actually define a variable that would contain something. So in this case, we always need to use the implement. And if we now here make a derived structure, I struct my data2 is equals my data2 derived from my data, and we add a another thing to it. Okay, so we have this thing, we make a pointer to it, mp data, just m data, p data. Then let's say we want to get rid of this at the end of the operation. So let's say here we don't use our release, we do not, this is not so important, we just delete it, and this should be of course null pointer. So one thing is, if we are in this init, we have no way to create like an object of type mdata2, obviously. So the earliest place where we could do it is here, mdata2, and let's set it to something. And that's already one thing. We want to access this as mdata2, so let's do it like this. Now we can access all the three thingies. Set A, B, and C. Okay, and so we create this here in the second constructor, but we delete it here. And here the data type is of type mdata. We are not aware of the other type. So let's see how this will end up. So we are here. We enter it. We enter the destructor of string 1. We can actually go a smidge deeper. But now we have already did it. The annoying thing is that if you have if you do the very first step in, then that this object and other things will not yet be displayed here as valid. And once you already step further, then we already make delete on data, which invalidates it as well. So this is a bit annoying, but just trust me. So we did the delete for this one, then we continue. Wait, we should have done it twice because we have two elements. Let's try it again. So we go into this thing, we get out, we get in. That's annoying. Let's do it differently. The debugger in the latest version of Visual Studio is sometimes a bit. Oh wait, I think I know why it might work. They changed a lot of things about how this works. So again, we go in, we go out. It doesn't work. Okay. I will just put a breakpoint on the destructor of the string destructor. This will give us the same thing. So, but before we do that, I will also add a few more breakpoints. We'll put a breakpoint here and a breakpoint there. Right. So we enter here, then we come to the one destructor. Now I pressed F5. Wait, you should see it. So, again, we are here. We see the address of this. Now I press wait, yeah. Now I press F5 so that we. Maybe I should just press then you see it because it doesn't my keyboard. We are entering this destructor. I can jump out of that. I can just continue actually. I continue too much. Let's try it again. Okay, so we are before we start anything, we are in the first breakpoint and continue. We enter the string 1, the string A destructor. Now when I play, we enter the string 2 destructor. So and then when I play, we are out. And the problem is that when we allocated it, if we now if I remove this delete from here and put it in our C2 destructor, and of course, since I know the type, cast to the right type. Okay, breakpoint, breakpoint, then we'll arrive in the string breakpoints 3 times for the A, B, and C string. So again, we arrive here, string A, now I press, string B, now I press again, string C, I press again, we are done. So we might have a situation where we would have a data structure like this one, where we would want to clean it up properly, but we would maybe want to keep it valid and not clean it up from here, but to have it cleaned up from there for some reason. For example, if here some operation with it and its A and B function values is supposed to still be performed. And in such a scenario, we could use this release function and pass then this thing to it. So, for example, this release, we could make it that it takes C1 as a parameter. Release here takes C1 as parameter. That needs to be here as well. And then instead of deleting, don't do this. And here we would run release this. And now in release, right, so the release 1, the one that is not knowing what it's doing. Do this. And right. Oh, I forgot the name. Pointer P. Let's see. I could actually call it. It is customary if you have any sort of static functions on a class, which then will get a pointer to the class in some way. Often would that would be when they, for example, are entry points for a thread. Then you would call the variable this with a capital T, and then this just works just fine without any conflicts. Okay, so we have our C1. Then we need to go to our release implementation number 2, and here we more or less just do the same, just with the right typecast. Zack. This can be 2 lines so that everything looks the same, and we don't care for the construct. Right. This release, of course, not a friend of the other one. So we should add here some sort of get function or make this thing public. For simplicity, let's just make it public for now. Now it's fine. And now when we run it, I won't demonstrate it because although I should. That's an easier way to do it. I will just add here a printf, and that's it. Then we can just look in the console what happened, and are not reliant on stepping through the debugger and not mispressing any buttons that force us to repeat the whole thing. Right, so where were we here? So I will go to C2. Right, and we forgot in C2 to do this. No, we did not. It's not here. I will comment this out so we see again the failure case. So we see C1 init. It initialized 3 of them, but it deinitialized only 2 of them. And now if we uncomment our other release function, now we will enter the C2. Then, as you see, we properly deallocate all of them. Now, this obviously sounds like a bit of a problematic situation with regard to generally assigning derived objects to members of the parent class, but in fact normally this would not be necessary, because normally what one would do is would just make here the destructor virtual, and this will already take care for it. So now with the virtual destructor, even if we run into this delete function, which is unaware of the MyData2, it will properly, once the destructor is invoked, invoke all three of the destructors. So the situation where you really would need an own cleanup somehow implemented in the parent class are rather rare. So if the object which you are working with, if you have control over it, then you can make it just virtual, and voila. Situations where you would not have control over the object might be if you are using some sort of library which provides you, which comes, for example, only as a header in the library. You don't have the source code for the actual functions themselves, so you cannot change anything about the interface, and the interface was not defined virtual. Then you will not be able to make it virtual unless you would do such more exotic workarounds as we did here with this custom release function. And conceptually, this is really not very different than how this normal virtual function mechanism works, just that we have a custom that we used a custom pointer and used it in a non-standard way. And I think we are running out of time, so I think this is a good place to stop this whole thing. During the next lecture we'll go back to our Qt, and I will show you maybe how to implement a custom model view approach to populating a tree view. This is quite useful with larger data sets, and it also falls under the category of general programming patterns that you might encounter in different other languages. So this model view model approach is, for example, used in C# with the XAML UI quite a lot. Although there it's a bit more complicated. Here the way Qt does it is a bit of a simpler approach, and for our needs good enough. Right. I should think of some homework for you, because still we haven't had any, and I think from what we did today there isn't really a good opportunity to make something out of it, although maybe one thing that wouldn't be too difficult. When we go to our panel thingy, we could as a task just try to move the TCP and, let's say, the demo device, because the test device, I think that does nothing. So move those two devices into actual DLLs. That should be reasonably easy with what we have trained here. So let's do that. Because already 2 lectures without exercises, without homework, that would be too much. Okay, so this we can get rid of. (29) 11 2024. TCP device and demo device C. good. I think this should be doable. It will be mostly just copying and pasting around and testing, and of course not forget to load the things. So somewhere, well, it will be a little bit more exciting because you have the that I should write it down so you don't miss this part. The more details, the better. So notes. Both the device class and the VLL on start cPanel data. Panel data should get from them the so basically you will have like a function give me the factory, like in our plugin we have like here we have make plugin, you would have instead of make plugin you would have get factory. So this will be plugin interf. No, this will be abstract factory. Abstract factory get factory. And where did we initialize this? Right, and here in Enum devices you just load the DLS and add the factories to the list, and then the factories would then generate the other internal objects. And since we are using here Qt, you don't and the Qt will enforce strong restrictions on what we can and cannot do with regard to interoperability. Basically, with this way, we only can use plugins which were built with the same Qt, with the same exact Qt version, and this is fine. So, what I want to say is, at this point, you don't need to do this this approach with like a string constructor that you then pass into it and so on. So I should write this here also as a note. No restricts limits the compatibility to let's be more precise with binary compatible Qt version. Fully abstract, but it would be nice to use for and other Qt projects. Right. So if you are creating some own thingy, then you should still use the abstract interface pattern, so that at least between different versions of your product, as long as you don't change the Qt version, the compatibility will be maintained. Yeah, good. Any questions? Okay, if there are no questions, then I'll upload the things to the model, and we will see each other in a week. Have a nice weekend. Bye bye.